And somebody is chatting with me. Great. Okay. Thanks. All right. All right. So this was a problem you guys are working on in groups, right? Outside of at the end of class, correct? Remember it? CEOs, tall CEOs. Okay. So, but we didn't go over it, did we? We didn't go over it. Good. Okay. We're going to do that right now. And yeah, I will do that. I will send this video to everybody. Because it's going to be better than the video I did yesterday for stats class. I kind of blew it yesterday in stats. I made a mistake. I hate it when I do that, especially when it's recorded. Okay, so psychologists thought that that taller people are more respected, and he made a hypothesis. Good word, hypothesis. Made a hypothesis that chief executive officers, CEOs of American companies tend to be, so these words right here, tend to be, when you see that, think center. They're talking center. They're thinking tend to be center, not centen. They're talking about, you know, tend to be like if they're relating it to the average. And they're saying they tend to be taller than the average height of 69 inches for an adult American male. And she investigated this hypothesis by recording the heights for a random sample, very important that it's a random sample, of 100 male CEOs. So we're going to ask a question. What term applies to the number 100? Naturally, I pick Alondra, who is not here. So maybe I can pick Karina, who's also not here. Let's see. What do you think? No, Reina. What term applies to the number 100, Reina? Are you there? Oh, there you are. Good.
Yes, I am not sure.
Okay, hang on. You'll be sure in a minute. There we go. Now I got Karina. Okay, so we took care of those two. They're done. They're done for the day. Oh, wait, somebody's coming in. No, somebody got knocked out and then came back in. Isa, do you know what term I apply to the number 100 in this example?
No, I do not.
Okay, we'll give one more try. One more try. This is an important concept. Alexi, do you know what term we apply to this number 100?
Was it random sample? I'm sorry, I don't remember.
Okay, everybody, close attention. This is the sample size. We took a random sample of 100 American male adults. How many male American CEOs were in my sample? 100. That's my sample size. So that is represented by N. N equals 100. That is my sample size. It's very important to kind of get that straight because, well, we know sample size, larger the sample size, less the variability. So that's going to have a big impact on your results. So you need to do some practice so you make sure you know what N is. Okay. Now, what is the population and parameter of interest in this study? In other words, why am I even bothering to do this? What am I trying to find out, and about whom am I trying to find this out? So what is the population that we're trying to find something out about here? Juliana, do you know?
I said it was the average height.
Of what?
Of the American CEOs.
Yes. Okay. So we got that is the parameter that we're looking for, is the average height. But in the population that we are trying to find out about is American CEOs, American male CEOs, which of course is almost redundancy, you know, but But you'll fix that. All right, you'll fix that. All right, so did everybody understand the difference here? This is the population of interest, American male CEOs, and the parameter, the number we're looking for is their average height. So Juliana, what symbol do I use to represent this parameter? Oh, no, now you're upset. Why did he have to ask me that?
For the parameter?
Yeah, what symbol am I using for this parameter right here?
Is it p hat? Or is it
Close. What?
mu?
It's mu,
Okay.
because this is a parameter. P hat would be for the sample. Okay, when I'm dealing with a population, it's mu. Populations and parameters, they use the Greek letters. So mu for the mean and sigma for the standard deviation. Statistics, which are from samples, they would use p hat. Oh, you know what? You know what, Juliana? We made a mistake. I made a mistake. We both made a mistake. You made the mistake and I confirmed the mistake. Yeah, p hat and s for stats. It's not mu. Mu is a mean. Oh, wait a minute. I am trying to find the mean. It is mu. All right. I'm sorry. All right. So p hat is wrong. P hat is wrong. First, I would use x bar, right? That's the mean of the statistic. Thank you very much, Mr. Jenkins, for totally messing me up, but that's okay. Everybody follow me here? We okay? You got the handout, so it shouldn't throw you off too much. Okay, now, that's a lousy question. I'm not even gonna do that. Okay. Suppose the population mean height of all male CEOs is 69 inches. The same mean height as for American adult American males. In other words, CEOs are the same height as average adult American males. Okay. I would like to make a sampling distribution of the sample mean of my 100 CEOs and like a whole bunch of samples of 100 CEOs. I want to make a sampling distribution. In other words, I go into the population of American male CEOs and I pull out 100 of them and I find out how tall they are and I put that on a dot plot. And I pull out another 100 and I find out how tall they are and I put that on a dot plot. So that is going to give me a distribution. What can you tell me about that distribution? A couple things you can tell me for sure. Imani, can you tell me something about that distribution?
Will it be unimodal?
Unimodal and symmetric. Make sure you put those two together.
Okay.
Because, for example, Imani, this is unimodal, but that's skewed, right?
Yeah.
So unimodal and symmetric, or you could say it's going to be normally shaped. That's okay too. So unimodal and symmetric. What else can you tell me about this, Imani? Anything? There's something else you can tell me about it.
I don't know.
It's in the first sentence.
The population mean height of all male CEOs is 69 inches.
That's right. So it's telling us, well, the center right here is going to be 69. If that's what we assume, that it's 69, right? That's what they're assuming. They're saying, suppose that the population mean height of all male CEOs is 69 inches, the same as for all adult American males. Okay. But there's another piece of information that we need in order to finish drawing this chart that we love to draw. So here is our population mean. Here's 1, 2, 3 standard deviations, -1, -2, negative. What other piece of information do we need here? I'll take a volunteer. Yeah, Caitlin, what?
Do you need to calculate the standard deviation?
Well, not only do I need to calculate the standard deviation, they need to tell me what the standard deviation is. Right? I mean, I guess it's the same thing. Yes, I need to know the standard deviation. I need to know what the standard deviation is. And they didn't give me that information. So now they're giving it to me. They're saying, suppose that the standard deviation of heights of male CEOs is 3 inches. Okay, so I'm going to come back to my graph, and I'm going to do 72, 75, 78, 66. Don't write this down yet. 63 and 60. Is that right? How many people say yes, that's right? No, don't even tell me that. The answer is no, that is not right. Because that is the standard deviation for the entire population of American male CEOs, right? With a sample size of 1. It says, when it says, be really cautious on this, okay? This is going to come up on the test. I'm just warning, it's in there on the test. If I say the standard deviation of the heights of male CEOs is 3 inches, right? But when I go in and I pull out a random sample of 100, that's going to have a much smaller standard deviation. It's going to be much closer to the mean. The average height of 100 male CEOs is going to be much closer to the mean than the height of any individual CEO. Am I making sense here? I will be happy to repeat that numerous times, but we're okay with this? You want me to say it again? Yes, say it again. Okay. They're telling me the standard deviation of heights of male CEOs is 3 inches. So what they're saying is, if I grab one CEO, I'll do it on this. If I grab one CEO, there's a slight possibility that one CEO will be 60 inches tall. If I go in and I grab another male CEO, there's a better possibility that it'll be 66. Even a better probability that they'll be 69, since that's the average height of all male CEOs. And maybe I'll find one that's a 71, and I could actually make a whole nice dot plot that would look like this if I just go in and I take one CEO at a time. You okay with that? Okay, but I'm not taking one CEO at a time. I'm going into the population of CEOs and I'm pulling out 100 of them and I'm averaging their height. So if I would take the 100 people that I pulled out here, well, their average isn't going to be, it's very unlikely that I would have their average, an average of 60. The average is going to be much closer to the mean because I have a sample size of 100, not just one at a time. Am I making sense? Brooklyn, did it make a little more sense? Everybody? People who have their cameras off, you need to give me like a thumbs up or something that you're following me, okay? So I can know what you're doing, or you can turn your cameras on, which is even better. Okay, all right. So these numbers here are wrong. I can't use these numbers because these would be fine for the entire population, but I'm not doing it for the entire population. I'm doing it for a sample size of 100. So in order to find the standard deviation for my distribution of samples, I got to take my standard deviation of 3 and divide it by the square root of 100. In other words, take my standard deviation of the population and divide it by the square root of n. See, this is why knowing what n is so important, because that's what you're going to divide by, right? So so 3 divided by the square root of 100 is 0.3. Well, that's a big difference, isn't it? I mean, now my chart looks like this. It looks like now this is 69.3. This is 69.6. This is 69.9. And over here I have 68.7, 68.4, and 68.1. Did I do that right? Yes, I did. Okay. much narrower because I have a sample size of 100. I'm not looking at the distribution of the whole population. I'm looking at a distribution of samples of 100 from the population. I know I say that a whole bunch, but you really kind of got to think about what that's talking about. You know, like try waking up at 2 or 3 in the morning and then having that, like, what is it talking about, that sample size thing? You know, and dwell on that a little bit, you know. So, you know, it should really be bothering you if you're not quite getting it. If you're really not quite getting it and you want to talk about it, well, send me an email. We'll talk about it and go over it one-on-one. Okay. So this is what the distribution should look like, because they told me that the standard deviation in the population is 3 inches. Okay, so we made a sketch of this sampling distribution. We just did that a second ago. All right. Now we're getting to the kind of the important part of this concept here. Yeah, okay. The psychologist will be persuaded that the average height of CEOs is taller than 69 inches only if the sample mean CEO exceeds 69 inches by at least 2 standard deviations. So I'm going back here. And remember, the hypothesis was originally that CEOs are taller than the average American male, right? That's the hypothesis. CEOs are taller than the average American male. And she says, I am only going to believe that is true if my sample of 100 turns out that their average is 69.6 or greater. In other words, the average of my sample of 100 has to be at least 2 standard deviations above the mean in order for me to believe that that's true. Now, why would she say that? She would say that because we know that with the sampling distribution that 95% of American males, 95%, are going to fall between -2 and 2 standard deviations. Empirical rule, right? Empirical rule, right? And so 95% of all American males, if I took a sample of 100, would fall between 68.4 and 69.6. 95% of all samples of 100 are going to average out to somewhere between 68.4 and 69.6. So I am only going to believe that CEOs are special if they average more than 2 standard deviations. That's the only way I'm going to believe that they're special, because that would mean, yeah, I'm just going to leave it at that. They are outside of the 95th percentile. They are that much different. Now, question? Does that make sense? Want me to say it again? I'm happy to do it over again. You can put it in the chat. You can say it over again. No, we're feeling pretty comfortable with that. Okay. All right. Good. Good. Okay. Now it said do this thing over again with a sample size of 30 and a sample size of 100. We're just not going to do that. I think you guys can do that. You know, so I don't think we need to spend the extra time. Good practice for you to do. Get used to using different n's. N equals 30. N equals 100. Get used to that. But we're gonna end with that. Is that all right? Okay, it's a good practice problem though. Do it. So let's just summarize here. Topic 15. A common error, probably the most common error when working with the central limit theorem, is to forget to incorporate the sample size n into the standard deviation of the sample mean. That just happens over and over again, which is why I originally drew this wrong, right? I want you to see what it looks like when it's wrong, And then I want you to see what it looks like when it's right. You have to use that n in order to get the right standard deviation. When we have a large sample size, n greater than or equal to 30, we don't really need to worry about the shape of the underlying population. If n is less than 30, then the underlying population has to be normally shaped in order to use the central limit theorem. That is also an important qualification that you're going to see on the test. So be aware. Yeah, Megan, please.
So if n is less than 30, will we be told if the underlying population is normally distributed, or is there some like way we have to figure that out?
No, that's a really good question. You will either be told that the underlying population is normally distributed, or you will be given enough data to plot it and look at your own histogram and see if it looks unimodal and symmetric. Or if it doesn't say, then you just stop the problem right there. You say, I don't know if the population is normally distributed or not, so central limit theorem, I am not going to use it. That makes sense, everybody? Right? So yeah, so if you see a problem like that, and I'm throwing a little trick at you, you know, you might, I think I do that on one of the other tests. I kind of threw that at you as a little trick. You don't remember? Oh, good. I'm glad it didn't cause nightmares, you know. If I did, you know, it was a, you know, quarter point kind of a trick. Okay. Okay. So you will either be told or given information to find it, or if you're not, then no, can't use the central limit theorem. Okay. Now we're going to talk about confidence and significance in the next chapter. And now we know all this. I mean, you have the handout. Proportions are with categorical variables. If my underlying variable is categorical, I am dealing with proportions, and that means pi and p hat. If it's a mean, that is quantitative variables, and that only has to be n greater than or equal to 30. No. Okay, that is it for topic 15. So we're going to jump right into topic 16. Let's see, I'm going to stop recording.